Hello students, I hope you all are doing well. Now in this video, what we are going to understand is the meaning of the term center of gravity. What does this center of gravity depend on? The center of gravity of regular and irregular laminas or plates, and the importance of center of gravity in solving numericals based on moment of a force and principle of moments. Now please watch the video till the end because this is important. Okay, I'll be actually showing with an example, a numerical. So sometimes when the weight of the rule is given, it acts only as a distractor, provided the rule is placed at the center of gravity. Now, if the rule is not placed at the center of gravity, that is the time when the weight of the ruler comes into play in the numerical. Okay, sometimes the weight is given, which we have to use it in the sum, and sometimes we have to calculate the weight of the meter rule. So please do watch the entire video to understand this properly. Now, the first thing that we need to understand here is what is the meaning of the center of gravity. Now, in a simple language, if explained in the simplest possible way, it means it is a point where the entire weight of the body acts. Okay, and the resulting moment of all the forces acting about this point is zero. I'll show you with an example. Supposing I take this ruler, okay, I can balance it at one particular place. Now, you can see I'm cheating. I use two fingers here. With a little effort, it can be balanced on one finger also, as you can see. With a little more effort, you can balance it on your fingertip like this. Now, at that particular point, the entire weight of this body is acting. And you can see this ruler is made up of millions of masses, tiny particles are involved. So what happens here is the resultant moment. Now, supposing if this is the ruler, which has been balanced at its center of gravity, right? It's made up of numerous masses, and each mass is being attracted by the force of gravity. So there are millions of anti-clockwise movements being created on the left hand side, and again there are millions of clockwise movements. But at the center of gravity, they cancel out each other. The resultant movement, okay, is zero. This is the meaning of it. So center of gravity is where the entire weight of the body acts, and the resultant movement at this particular point is zero. Along this point is zero. Now the question arises, what does this center of gravity depend on? So let's see now. The center of gravity of any body depends on the distribution of mass in a body. Now, say for example, or in other words, in some books you'll find it's also written shape and size, shape of a body. Now let's try to understand this first. Supposing you had some play clay, okay, and you had this play clay in this shape. Where would the center of gravity be? At its geometrical center, right? At the center is the center of gravity. Now, if I was to change the shape of this clay, okay, I made it into a different shape. I get something here, and I put most of the thing this side. Now, the center of gravity will shift. It will shift towards where there is greater mass. So, see, the center of gravity depends on the distribution of mass in our body. Now, there are several examples to prove this also. Even in the case of our human body, our center of gravity is near the navel area, slightly higher up, because our mass is more on the top side, right? So, firstly, when we step onto a weighing machine, as long as our center of gravity is there, okay, aligned with the weighing machine, we get our perfect weight. The entire weight of the body is acting there. Now, you cannot cheat the machine. You cannot extend one hand outside and expect your weight to be less, or this hand outside weight will become less, or you put one leg outside. It's not going to help you at all. As long as the center of gravity is there on the weighing machine, we get the proper weight. Then, you have seen trucks, sometimes in the highway they are toppled over, accidents have happened. Why? Because they have been overloaded. Now, when you start overloading a truck, what will happen is the center of gravity gradually starts to shift up. You have increased the mass, so it starts to shift upwards, right? And that makes the truck unstable. So there are chances of it toppling over. Okay? Even for us, for our human body, since the center of gravity is slightly higher up, The mass is more this side. When somebody falls off a building, accidentally, if you trip and fall, you go head down first, and that is fatal. Not while jumping. While jumping, we take care that we jump in such a way that we protect our head, we land on our knees and hands. Elbows might break, the knee might break, but we try to protect our head. But accidentally, if you fall off a building or if you're pushed off a building, you go head down first. So center of gravity depends upon the distribution of mass in a body. It is always towards where there is greater mass, and it also, you can say, depends upon the shape and size of the body, shape of the body basically. Okay, but the important thing you'll keep in mind is it depends upon mass. Now let's see the center of gravity of regular and irregular laminars. Now for regular laminars, there's no problem. For regular plates or laminars, the center of gravity is not a problem. If it is a rectangular lamina, okay, the center of gravity will be where the diagonals intersect. So here you have your center of gravity. If it's a triangular lamina, where the medians intersect. So where the medians intersect, that's where you get your center of gravity. If it is a circular lamina, the center of gravity will be in the geometrical center. Now there are two exceptions, and you'll keep these exceptions in mind, where the center of gravity does not lie on the material of the body. For example, in the case of a circular ring. So if you have a circular ring like this, the center of gravity is still in the centermost portion, which does not lie on the material of the body. So this is one exception for a circular ring. And the second exception is in the case of a hollow sphere. Now, if you have a hollow sphere like a football, so the leather part, the bladder and all is there, right? The leather portion is there. Inside there is air. Now, in the center, okay, in the hollow part in the center where there is air present, that is where the center of gravity lies. Now, these two exceptions are very frequently asked in ICSE. So, for a circular ring and for a hollow sphere, the center of gravity does not lie on the material of the body. Okay, in these cases, it is on the material. So, these are for regular, meaning for regular laminas, it is at the geometrical center basically. Now, what happens if it is an irregular lamina? Now, to find the center of gravity of an irregular plate, we use what is known as the plumb line method. So, if it is an irregular lamina, say we have some shape and we wanted to find the center of gravity of this irregular shape, we use the plumb line method. Okay. Now, plumb line basically is a device used by those workers who deal with cement work, and when they are constructing walls and plastering walls and all, it is a metal piece, heavy metal piece pointed at one end, okay, like almost like a top pointed at one end and has a thread attached to it. So when they are constructing walls, when they're putting up walls, they hang this plumb line to see whether the wall is coming up straight or not. Okay, so this is a thread with a heavy metal piece attached at the bottom, pointed. So if you have a shape which is irregular, at least at three places we make three holes. This is A, this is B, and this is C. Right. So at three places we have made three different holes, and then we choose a nail in the wall. So we choose a nail and we hang this object through the first hole. Now I'll just show you. So here is an irregular shape, right? Now supposing, not too irregular, you can see. Now we choose a nail on the wall first, and I suspend this through hole A. Okay, it will move around for a while and finally come to rest. Now all we have to do is drop a plumb line and with a chalk mark the position of the thread over there. So supposing we got a mark like this, I call this as AX. Okay, then we turn the body and suspend it through hole B. Again we put it through hole B, and again it'll move around for a while, and then we hang a plumb line there. So through B, supposing we got a line this way, we call it as BY. Then finally we repeat it for C. Again, it'll come, move for a while and finally come to a stop. And we obtain the line there. Z. Now, where all the three lines intersect or are very close to each other, that is where the center of gravity of this material lies. So this is called the plumb line method, used for determining the center of gravity of an irregular plate or a lamina. Now, the importance of this center of gravity while solving numericals based on moment of force, this is very, very important. Why? Because now what will happen is you should be able to decide whether the weight of the rule is to be applied in a particular sum or not. Supposing they say the weight of the meter rule is 100 GF, okay, and there are many things given in the numerical. Now, if you read the sum and it says the meter rule is balanced at its midpoint, so supposing it's a full meter rule, 0 to 100 centimeter, and if they're saying it is balanced at the 50 centimeter mark, then this weight given to us is a distractor, meaning it is not going to affect any portion of your working because it is acting at the center of gravity. It plays no role. Okay, there is no, the force is there, but there's no distance here. So the torque produced by this force is zero. We ignore this. This is just a distractor in that case. But if the scenario changes, meaning if the meter rule is placed at any other mark, not at the 50 centimeter mark, say at the 70 centimeter mark, now the weight of the rule will come into play. Why? Because the weight of the ruler is acting at the center of gravity, meaning at the 50 centimeter mark, it is acting. So you cannot ignore it now. Now the 100 GF will come into play. And accordingly, you'll put the other things, whatever is provided in the sum, and then solve it. Okay. And we are going to understand this with a proper example. I'm going to put up a sum and show you the actual working, how we use this. Try to understand with the help of an example. Now, the sum that I put up here is a uniform meter rule is balanced at the 60 centimeter mark by suspending a weight of 100 GF at one end. Find the weight of the rule. So first, let's draw a small diagram to represent what is given to us. So this is a uniform meter rule from 0 to the 100 centimeter mark. Now they're saying this meter rule is balanced at the 60 centimeter mark. That means not at its center of gravity. So here is 60 centimeter mark. That's where it's being balanced. Now immediately what you'll do is, you know that the center of gravity is here. That means at the 50 centimeter mark, the weight of the ruler is acting. And we take that weight as W because the question says we have to find the weight of the rule. If the weight of the rule was given, we would have placed it here. And if the rule was balanced at the 50 centimeter mark, remember the weight of the ruler is not to be considered at all. Find the weight of the rule is the question. At one end, now 100 GF is suspended at one end. Now we do not have the option of just putting that 100 GF at any end, like in the previous sum. You cannot put it here because you'll have two moments created on both on the same side, and this rule is definitely going to fall. As it is falling because of its own weight. All right. So what we have to do is now place that weight which is given to us on the other side where the moment is not there. So 100 GF. Okay. And according to the question, now this is a balance scenario. Balance means anti-clockwise movement is equal to the clockwise movement. So in equilibrium, please don't forget to write all the statements. In equilibrium, anti-clockwise movement is equal to clockwise movement. Here, anti-clockwise is this. Because of the weight of the rule is falling this way. And on the other side, there is clockwise movement because of the given weight, the rule is falling this way. So let's see how much is the anti-clockwise movement. Force multiplied by the distance from the perpendicular distance from the axis of rotation. So we have W multiplied by the distance is 50 centimeters to 60 centimeters. The distance is 10 centimeter here. So 10 centimeter equals. We go to the clockwise side now. Force is 100 GF multiplied by the distance from the axis of rotation is 60 to 100. The distance is 40 centimeters. So keep in mind, these are the distances that we have to consider. Here, this distance, and here it is this distance that we are considering. Okay. So we have, now we just find out what is W. So W becomes 100 GF multiplied by 40 centimeters divided by 10 centimeters. So 10 divides it 4 times, 4 into 100, we are getting answer of 400 GF. So you can see in this particular question, since the meter rule was not balanced at its center of gravity, the weight of the ruler did come into play. If you want me to do more such numericals, please comment. Okay. We'll do more of these numericals in future videos. Thank you so much for watching. Please do like, subscribe the channel if you found it to be useful. Thank you.